In our last video, we talked about intermolecular forces, things like dispersion forces, dipole-dipole forces, hydrogen bonding, and ion-dipole bonding. In this section, we're going to talk about how those forces will allow particles to come together to form liquids or solids. Here we go. Basically, it works like this. If a substance has very little intermolecular attraction, then those are going to exist as gases. But a substance that has somewhat strong intermolecular attraction, those are going to be more like liquids. And if it has very strong intermolecular attraction, the substance is going to most likely be a solid. Kinetic molecular theory isn't just for gases. It also can explain to us how the particles are put together in solids and liquids. For instance, we know that a solid is going to have definite volume and shape. The particles are packed together in fixed positions, and they're not really that free to move. They'll have some vibrational motion, but not really much more than that. But if we add heat, we are adding kinetic energy, right? More kinetic energy, though, means that those particles are a little bit more free to move. They're able to kind of break that hold that those intermolecular forces have, keeping them in that rigid framework, and they're able to glide past one another. Still somewhat close together, so we say that they have a definite volume, but an indefinite shape. They take on the shape of their container. The particles are close together, but not in a fixed position. They're free to move around. But gases have neither a definite volume nor a definite shape. Those particles are separated from each other with great distances, relatively speaking, and those particles are very much free to move. One of the concepts we talked about previously was that of density, and we said that, in general, gases are about 1,000 times less dense than their liquid or solid counterparts. Liquid water is about 1,250 times more dense than water vapor is. Because those particles are much closer together in the liquid and solid states, we consider them to be incompressible. There's no real empty space to compress those particles together. That might be easy to see and understand with solids, but it takes an enormous amount of pressure to compress a liquid, to reduce the volume of that liquid even by a small amount. Let's talk about some other characteristics of liquids. One of the characteristics that they share with gases is that of being fluid, fluidity. It just simply means that gases and liquids have the ability to flow. Now, because liquids have more intermolecular attractions at work, they diffuse less rapidly than gases do, and they flow less rapidly. So liquids then are less fluid than gases. How about the term viscosity? Have you heard that one before? Viscosity is just the measure of a liquid's resistance to flow. A couple of things determine how much viscosity a liquid will have. One would be the amount of intermolecular forces at work. Two would be the size and shape of the molecules. And a third one would be temperature. It's easy to see, for example, this sample of water that's easy to flow, very low viscosity. Yes, you do have hydrogen bonding going on between the water molecules, but the water molecules themselves fairly small. That's why you have a very low viscosity. On the other hand, we have slime in this container. You may recall we made this slime by taking glue, which is composed of long chains of carbons, and we cause those chains to cross-link. So in other words, we're linking chains to chains. That makes for an enormous size molecule. And the larger the molecule like this, the more resistant it's going to be to flow. That's why this slime takes a very long time to pour from this container to the table. Yeah, we're going to have to move on. But the whole particle size makes sense, doesn't it? Remember back when we were talking about gases and how fast they diffuse or effuse, we said speedboat cruise ship, right? Well, the same kind of holds true. The larger the molecule in a liquid, the more slowly it's going to move, the more viscous it will be. The third factor when dealing with viscosity is temperature. And what we find is that viscosity decreases with temperature. As temperature increases, viscosity decreases. If you take a jar of honey and put it outside in the cold weather, it's going to get very viscous. It will be extremely thick. But if you take that same bottle of honey and place it in the microwave for a little bit, it's going to become much less viscous, right? It'll be much easier for that honey to flow. So the higher the temperature, the lower the viscosity. Another characteristic of a liquid is that of surface tension. When you have molecules in a sample of liquid, we find that those particles that are in the middle of that sample of liquid can be attracted to particles all around them, right? Top, bottom, sides, and so forth. But for particles that are on the surface of the liquid, they don't have any attractive forces above them to counter the attractive forces below them. So that causes the surface area to be pulled together more tightly, like the head of a drum. For that surface area to increase, particles from below the surface have to move upward toward the surface. It takes energy to overcome those attractive forces that are holding those particles in the interior portion of that sample. We call this energy surface tension. It's the energy that's required to increase that surface area by a given amount. So really, surface tension is a measure of the pull that those interior particles have on the surface particles. And as you might guess, the stronger the attractive forces, the stronger the surface tension. Water has a great deal of surface tension, and it's what allows little tiny bugs and so forth to be able to just sit on top of the water and not be pulled into the water. Sometimes the surface tension of water can be a difficult thing because it's the reason why dirt doesn't just readily come off when you wash it with water. You see, the dirt particles can't really penetrate the surface of that water because of the surface tension. So to solve that, we use soaps and detergents. Those soaps and detergents break up the hydrogen bonding that's taking place between those water molecules, and then the water spreads out and allows the dirt to be carried away by the water. A compound that lowers the surface tension of water like that is called a surfactant. Another characteristic we see of liquids is cohesion and adhesion. We've seen this before when we put water in a narrow glass tube, like this graduated cylinder, and we notice that the surface of the water is not straight. The surface forms a concave meniscus, as it's called, and what's happening are two distinct sets of forces. One is cohesion and the other is adhesion. Cohesion is what happens between molecules that are alike, in other words, water molecule to water molecule, and adhesion describes the force of attraction between unlike molecules, the water with the glass in this case. It just so happens that the adhesive forces of water with silicon dioxide that's in this glass are stronger than the cohesive forces between water molecules. So because of that, the water tends to creep up on the sides there, forming that concave meniscus. Incidentally, if that cylinder is extremely narrow, the water will actually be drawn upward into it. The movement of a liquid inside one of those very narrow tubes is called capillary action. It's the reason why paper towels can draw up water so well. The water is drawn into the narrow gaps between the cellulose fibers of that paper towel. That's capillary action. So those adhesive forces allow water to be drawn up in that fashion. This is the reason why water is able to be drawn up into the roots and stems of plants and trees. Now, as we know, solids have a definite shape and definite volume because those particles are closely packed together and held in place by intermolecular forces. They have some vibrational motion, but that's about it. Because of that, in general, solids are more densely packed than liquids are, so usually solids are more dense than liquids are. An obvious exception to this is, of course, water, where the solid form of H2O, ice, is less dense than the liquid form. But again, usually if you have solid and liquid states coexisting in the same container, the solid state usually sinks to the bottom. It's about 10% more dense than the liquid counterpart. Usually we find that the molecules within a solid are arranged in a very predictable pattern. We call this a crystalline solid. It's a solid whose atoms or ions or molecules, for that matter, are arranged in an orderly geometric structure. We can easily see this with sodium chloride that takes on a very cubic shape. We have the repetition of sodium ions, chloride ions, over and over again in all directions, forming that cube shape that we see. Remember, we've talked in the past about crystal lattices, and that's an example of a crystalline solid. Within that crystal lattice is what we call a unit cell. It's the smallest arrangement of atoms in that crystal lattice that has the same type of geometric symmetry as the entire crystal. So it's like a building block, and we really have all types of unit cell shapes, from cubic shapes to more hexagonal shapes, rhomboidal shapes, and on and on. We classify crystalline solids into 5 distinct categories, and that's based on the types of particles they contain and also the arrangement of those particles. We have atomic solids, molecular solids, covalent network solids, ionic solids, and metallic solids. The only atomic solids we have are noble gases. Yeah, they have to be really, really cold to do it, obviously, extremely cold. Atomic solids are soft or even very soft. They have extremely low melting points and they have very poor conductivity. Molecular solids can be held together by dispersion forces, dipole-dipole bonding, or even hydrogen bonding. A lot of molecular compounds are not solids at room temperature. Water, of course, is a molecular compound and it's a liquid at room temperature. But when you get to larger molar masses, like say sugars and larger carbohydrates, you do tend to have solids in that case. Again, remember, the larger the molecule, the more opportunities there are for intermolecular forces. Thus, more opportunities for solids. Molecular solids are usually soft, they have low to moderately high melting points, but because there's no ions involved, they are poor conductors of electricity. Some solids are what we call covalent network solids. Carbon, for example, can form multiple covalent bonds. Because of that, carbon will form several different types of covalent solids. Diamond, for example, graphite, another one called Buckminster fullerene. No kidding. Anytime you have an element like carbon that exists in different forms within the same state, whether it be a solid, liquid, or gas, we call that an allotrope. Covalent networks are very hard. They have high melting points, but they're still pretty low on the conductivity scale. Ionic solids exist where you have a network of positive ions surrounded by negative ions. Remember that? Because of all the charges between ions in an ionic compound, they're very hard, they have high melting points, but they're also very brittle. And they're only conductive if you dissolve them in water. As we talked about in the last section of Chapter 7, metallic compounds have that sea of electrons around the metallic cations, making them very malleable and ductile. They're extremely good conductors of electricity. Some metals are soft while others are very hard, and they can vary in their melting points, some being low, others being very high. Again, those 5 were all types of crystalline solids, one main category of solids. The other main category we'll talk about is that of amorphous solids. In an amorphous solid, the particles are not arranged in a nice geometric pattern, but rather haphazardly. Some are clustered together more closely, and others more spread apart. Examples of this would be glass, or rubber, or even some plastics. That's all we're talking about for today. In this video, we focused on the characteristics of liquids and solids, how the kinetic molecular theory explains the particles arranged in those liquids and solids, and some of the characteristics of each. Hope it's been helpful to you, and in our next video, we'll talk about phase diagrams, the changes from solids to liquids and gases, and how we can show that graphically through a phase diagram. Until next time, God bless.